I need I need something that holds the block in place, to holds it where it is. So what's that?
It's just floating.
So, well, somebody thought it was attached to another cord. That doesn't change the problem at all, as long as it's at rest relative to the other block. So there's going to be this condition where the block will have swung down to the same level as the block that's on the table, like so, and has not, but is about to strike the first block. So at this moment, this block has a velocity, but has not struck the second block. Fair enough? Then there is the condition where both blocks are now stuck together and are essentially one block, right? They're stuck together, so they move together. But they have not yet begun to swing. So they have a combined velocity, but this is instantaneously after they stick together. And then there's the part where it's swung upwards and comes to rest for a second. You guys see all this? The maximum displacement or the maximum angle in the problem. Now, I'm breaking it up into meticulous detail because you have to figure out what is being conserved as we go from place to place here. And that's why I've set it all up like this. And your problem probably only has maybe, if you have one with a picture, maybe this picture and this picture, or I only have two of these at best, or only one. And you have to imagine the whole problem. For the time being, it might be in your best interest to kind of sketch out what's happening. And you don't have to be as meticulous as I've been here, but it will help you in understanding what's happening. So from here to here, I'm noticing that a single object is moving, and that object is changing height, going from rest to some velocity at the very bottom. That's got to be conservation of energy. Now, this is a collision, so it's not conservation of energy unless they tell me it's elastic. It sticks together, which is a big indicator it's not elastic. So it is definitely going to be conservation of momentum because it's a collision. All collisions conserve momentum. But this only accounts for the instantaneous moment before contact and the instantaneous moment after contact. You have to be very careful there. There are forces acting on this system which do change its energy. So the collision part is only those two instances. But I bet it does lose energy because it's an inelastic collision, which means that from here to here, though, it's a single object that swings upward from its lowest position. That's got to be conservation of energy. This problem has that flow to it. I'm going to do a conservation of energy problem first, a conservation momentum problem after, and a conservation of energy problem last. You should lay your problems out like this. If you want success, if you want to stop getting Fs, you should lay your problems out like this. In fact, I'm probably unwilling to help people who won't lay them out. Now, in saying that, I'm going to point out that I have gravitational potential energy here equal to mgl. That's how much energy I think I have. Any question about that? Over here, I'm going to have all kinetic energy, 1/2 mv squared. Now the object actually has mass of 2m. So let's put this together. 2mgl equals 1/2 times 2mv squared. This will help me figure out how fast it's going just before the collision. I don't think I was asked that, but there's a collision. Collisions are all about momentum, which is all about velocity. In the collision, the momentum of box 1 has to be equal to the combined momentum of box 1 and box 2. That has to be true. Because it's a collision, momentum must be conserved. So 2mv has to be equal to 2m plus m v final. I say v final just to have some way of differentiating the velocity before the collision to the velocity after the collision. But now this system has energy. What kind of energy? Kinetic. It's less than it had before, I'm sure of it. And on a real exam, I would ask how much less. But in this problem, that kinetic energy is going to be converted into gravitational potential energy, lifting the box some height off the table. But I don't want the height, I want the angle. So I need to also bring into my recollection that getting the angle from the height is going to involve the length of the string. I'm going to have to use all of these things here. I'm thinking over here, it's going to be 1/2 times 3m v final squared equals mg, not m, 3m g L times 1 minus cosine theta. I see this as my roadmap for what I'm going to have to do. And since I was given all the information at the very beginning, I think I'm going to go from left to right here. I'm saying that because they don't have to do that. They could tell you how far it swung upwards all the way at the other end and ask you the mass of the first box. Follow what I'm saying? They don't have to do it this way. This problem has been presented to you in a very linear fashion and can be executed in the order of the operation. Don't assume that that's the way it's going to be on tomorrow's test or on the AP exam. They could definitely ask these questions out of order. But okay, are you guys ready to begin, or is that enough information to execute the problem? I don't even know who asked, so that's why I'm asking. Yeah, I'd be happy to. Cancel out the 2m's, which is going to give me a velocity equal to the square root of 2gl, which becomes the velocity here, 2m times the square root of 2gl equals 3m vf. The m's cancel, but it does tell me that the final velocity is going to be equal to 2/3 the original velocity. Now, the reason it's 2/3 is because the box that had the original amount of momentum was heavier. Because it was heavier, it carries more of the momentum through the problem. If I had reversed that, had the box be the single m and the other one was a 2m, it would be 1/3. So whatever has the more mass tends to determine the end result of the momentum. So that's why we get 2/3 of it. Now, that means that over here, and I'm going to run out of space, so I need to, that's a disappointment. But that's not. So in doing the last part, I'm going to have 1/2 times 3m times 2/3 times the square root of 2gl squared equals 3mgl times 1 minus cosine theta. And here's where a lot of students make mistakes. And so this is worth kind of playing it up. I can cancel out the 3m. That's not going to be a problem. I'm going to have 1/2 times 4/9 times 2gl equals gl times 1 minus cosine theta. So here, cancel out the GLs. Let's run the numbers here. The 1/2 and the 2 cancel out. So I get 4/9 equals 1 minus cosine theta. So cosine theta is equal to 5/9. I didn't cancel out, but it became 1. Oh yeah. Shelton for the score. So I like that question. Good stuff. What I like best about the question is I could ask now, like, what's the ratio of the final energy to the initial energy or something like that. There's a lot of good stuff that can be asked here. I'm a big fan of this question, by the way, big fan. So you should be too. I like it because it's relatively straightforward once you've seen it done once. Now, it doesn't have to be this. What if instead of them, sticking together and staying on the cord breaks and this is the edge of the table and they become a projectile? Or what if I want the system to go a certain distance and after it's a projectile and I ask you how far do you have to pull it up for it to make that distance? That's fine too. These are all the same question in that you're going to have a combination of a conservation of energy and a conservation of momentum question. So you need to kind of figure out where the limiting factors and what direction it is you need to do the problem. Laying it all out kind of tells you which state of the problem you know about. I would encourage you to lay the problem out so you can look at what's been given and figure out where in that problem you've been given the information to complete one state. But they have to give you enough information to get one state of the problem. We were given the initial energy of the problem and the fact that they stuck together. Those two things are what we really needed. All right. Which one next? 5, 3. Which one's 3? Which one do I want to do next? Oh, 5's not terrible until you get to part D and E. And let's be honest, you can't do 5 part D and E unless you can do which one is it? Number 4. Yeah. So 4 and 5 D and E are very similar. So let's take a look at 4. And the reason why I look at 4 is because question 5, A, B, and C are not so terrible. Let's do that. Let's do that part. But then I want to talk about something a little different. Because that 8 kilogram block is against a backstop for A, B, and C, it never moves, which means it's not part of this problem at all. The spring is going to be part of the problem. The 2 kilogram is going to be part of the problem. And the 0.1 kilogram ball of clay is part of the problem. So let's focus on those things for just a minute. I see a ball of clay approaching a box that is attached to a spring. There's going to be a moment where the ball of clay and the box collide. That happens first. And I assume the ball of clay sticks to the box. Does it? Or does it bounce off? So this system is going to have a combined velocity to the right. But then this system, being a combined velocity and being stuck together, is going to compress the spring some distance, x, coming to rest. I haven't even read the problem, but that's got to be what happens. So when I look at this problem, I see a transition from here to here. What's conserved? It's got to be momentum. Got to be. It's collision. There's an instantaneous before and instantaneous after. But then it's a single object that seems to compress a spring. That's got to be conservation of energy. Now, I don't know what they've given us to work with, but I do see numbers. So let's see. I bet I don't have the velocity of the ball of clay, but I don't know. What do I have? K is 200. What do I have? Tell me.
Displacement and the mass for everything.
How far is the spring displaced? How many?
40 centimeters.
So it seems to me that I know the energy at the end. That the energy at the end is 1/2 kx squared. That's how much energy the system has at the end. I think I can figure out how much energy the system had after the collision. They had to be equal. This would be the final velocity that occurs right after the collision. And there's going to be the combined mass of the clay and the box times this velocity. But before that, it's just going to be the mass of the clay times its velocity. working the problem backwards, but it's the same problem. I will need to take this velocity, plug it in here, and work backwards to get the velocity of the clay ahead of time. Ready for me to go? Or can you do the numbers yourself? Be honest, I am indifferent. So you're saying we're good? Excellent. Do you see how laying it out really makes it pretty clear? I would really encourage you to lay it out, because once it's laid out for you, I'm hoping you'll have an easier time figuring out when energy is conserved, when momentum is conserved. But be forewarned about this. Collisions are fast. They will try to distract you from the collision part, but collisions are fast. We're looking at instantaneously before and instantaneously after. Doesn't matter how far back the ball starts. We don't actually care about that moment. The truth is, we don't care about what happened until the ball got right here. So they might make it look like there's all this stuff that could happen before. Be careful about what the problem is really trying to get you to focus on. But D and E pose a problem, don't they? So let's talk about that problem. For this one, I'm really going to refer to question number 4. Not question number 4. Question number 4. Because it's a cleaner version of this question. It doesn't have a lot of distraction. There's not this ball of clay. And I'm not going to draw it in a linear fashion. I'm going to draw it vertically, the different states of the question. So up here, the way this problem begins is I have a block that is approaching another block, but this block has an uncompressed spring, and this one has velocity. Good? So there's going to be the moment where there's no friction. There's going to be the moment where the first block, still moving, contacts the spring, but hasn't begun to compress the spring yet. So it has velocity, the same velocity it had a moment before, but hasn't begun to compress the spring. And then there's going to be this point where the spring is compressed, but both of the things are moving. And that's probably what you're wondering. Like, I've had several questions like, why would it compress the spring? Because there's no friction. I've heard that before. And I've heard a few things, but let's talk a little bit about what's actually happening here. But do I have the state of the problem kind of laid out? Nothing really happens from here to here. I just want to have this extra space in here to talk about this. The first box has velocity, therefore it has momentum. In fact, it carries the momentum of the system. Momentum has to be conserved. This is a collision, which means the momentum of the system here has to be equal to the momentum of the system here. We have no idea how fast either of these boxes are moving, and the spring is compressed. However, Amanda's in the waiting room. She must have got thrown out. However, you need to understand what's really going on. The moment the first box touches the spring, there's instantaneously going to there's going to be a force on the first block from the compression of the spring. But there's also going to be a force on the left block from the compression of the spring. This force begins the process of speeding up the right block and slowing down the left block. But that's not going to happen immediately. So the spring compresses some because the left block is moving and the right block hasn't begun to, which makes the force bigger, causing a larger force on this block, accelerating it faster, while at the same time creating a bigger force over here, slowing it down faster. Now, do you understand that spring is going to continue to compress until a certain condition is met? What condition has to be met for the spring to stop compressing? I have one hand, two hands, 3, 4, 5, 6, 7, 8. All right, 8 people think they know. I'm glad to see that there's some stuff out there. Let's go with Lauren.
I think it's equilibrium.
Okay, what do you mean by equilibrium? How many of you agree with Lauren that's at equilibrium that happens? All right, so one person agrees. All right. It's not. And it's because the spring's already in equilibrium before the box strikes it. Equilibrium is when the net force is 0. And in this circumstance, the net force is 0 on the spring. It's in its relaxed state. We get equilibrium in other conditions because there's another force like gravity causing the spring to reach equilibrium. But we don't have that problem here. The spring keeps compressing until, Luke? The velocity of the two boxes are equal. That's right. As long as the right block is going slower than the left block, then the left block is going to keep compressing the spring. But the moment both blocks have the same velocity, then the spring is at its maximum compression, because after that, the right block is going to speed up and now be going faster than the left block. And thus the spring starts to stretch again. Everybody follow that argument a bit? The point, and you might want to write this down, the point when both blocks have the same velocity is the maximum compression of the spring. It's a perfectly inelastic collision at that moment. It won't stay like that. It's going to happen only for an instant. But at that instant, both blocks are joined together and we have 2m plus m has to be equal to this final velocity. This does not tell us how much the spring is compressed. It just tells us the condition when the spring is at its maximum compression. So we started out with 2m times v as the initial momentum of the system, and that has to equal 2m plus m times v final. All this tells us is how fast they're going. But it's a frictionless surface. And although this is not an elastic collision, which would conserve kinetic energy, it still conserves energy if there's no external force on the system. Therefore, 1/2 kx squared for the spring plus 1/2 times 3m times v final squared for the boxes. They have kinetic energy. Has to equal 1/2 times 2m v squared for the original energy the system had. Energy is conserved because nothing took it out of the system. Once you find out what this final velocity is, you can substitute it here to figure out the maximum compression of the spring. That's how you do both problems. That's how you do both problems. It's a great question. I love this question. I love it for a number of reasons, because imagine this version of the same question. One of my favorites. It's a block fired at a wedge on a frictionless surface. It's a classic question. When it strikes the wedge, it does the same thing we just described, except it climbs up the wedge, storing gravitational potential energy, but it's still a collision. It's the exact same problem we just saw, except that instead of having elastic potential energy, there'll be mgh plus the kinetic energy of the two objects equals the kinetic energy that was here before. It's the exact same question. And they've given both on different exams over different years. But it's a great question. It's a great question. But I also need to point out one more thing here, and this is important. The momentum of the center of mass of this system never changed. Spring or no spring, the momentum of the center of mass of the system never changed. And there is something that I think bears witness that you should see before I let you ask me another question, and that has to do with, what does that mean? If I wanted to find the center of mass of the system, it would have been m1x1 plus m2x2 over m1 plus m2, correct? What's the derivative of this with respect to time? This is the velocity of the center of mass. You just take the derivative of the position. But if you're really paying attention, I know you're not because you can't see it the way I see it because I've done this 20 billion times. The velocity of the center of mass is always the same as the velocity of a perfectly inelastic collision. Always. That is the velocity of the center of mass. So believe it or not, that's the velocity that the system had before and after the collision. Whether they're separated, whether they're together, the velocity of the center of mass would be the velocity of a perfectly inelastic collision. I would memorize that before tomorrow's, I don't know if it's on test or not tomorrow, to be honest. If it is, it's in the multiple choice. But the velocity of the center of mass is the result you would get for the velocity of a perfectly inelastic collision. Wow. Physics, so exciting. So do you want me to do D and E or do you want me to do something else? Oh, question 3 is pretty good. We should talk about question 3. Do we have time? We have time. We have how many minutes? Woohoo! 3 minutes. Number 3 hinges on you knowing when the block would separate. Wouldn't you agree? So we have the spring with nothing on it. If I put the 5 kilogram box on it and let it come to equilibrium, I don't drop it, I let it come to natural equilibrium, it will sink from its original state downwards 5 centimeters. If you use mg equals kx. If I add the 3 kilogram block and let it come to rest at its natural equilibrium will be 8 centimeters. Mk equals kx. Everybody okay? So I push the block down and let it go into oscillatory motion, meaning it comes down, it comes back up, it keeps moving back and forth. When does the top block leave the bottom? Max? Sure, that has to be true, but what condition has to be met for them to separate? You can keep going, Max.
When the acceleration from the spring is more than gravity.
That's the important detail. And for you guys at home didn't hear that, the time that they separate is when the downwards acceleration is greater than g. The box can endure that because something is pulling it down, the 5 kilogram box. It's attached to a spring. So the 5 kilogram box, it's okay. It's attached to the spring. It can accelerate downwards more than g because it's got gravity pulling it down plus the spring. But the box that's resting on top, it doesn't have those things. If the box below it accelerates faster than g, the box on top separates. That's our limiting factor. And when does that happen? When this system makes it here. That's when it happens. Because if it goes any higher than that, the spring will pull down on the block, adding to the weight. So that's our limit. We can't go any higher than that position. So instead of seeing how far down do you have to pull the blocks, start by pulling the blocks up to here and see when you release them, how far do they go before they come to rest? Conservation of energy should work in both directions. So give it the gravitational potential energy and see where that energy takes it in the form of elastic. By the way, this will give you h, the total distance. That's not the answer. The answer is how far from here it has to be pulled downwards. So you'll have to subtract the original equilibrium position. It's 8 centimeters, by the way. It's 8 centimeters is the answer. All right, folks. Wow, that was a lot of fun. I enjoyed that immensely because, you know, it's physics. And, well, let's just say that this is the